Hi guys, and apologies for releasing this video a little bit later than usual. I really had a lot of work. But today we are going to look at two problems from AtCoder beginner contests that I think are... One of them is very common technique that you should know, like especially if you're preparing for some kind of job interviews. That's really common. And the other one is not that common in interviews, but more of a competitive trick that we are going to discuss in greater detail. So let's start with the easier one. It comes from ABC 214, and that is problem E, packing under range regulations. As you can see, it consists of several test cases, but that's of not much interest. What is interesting is that we have 10 to the 9th boxes and n balls. We want to put the balls into the boxes in such a way that i's ball gets into a box between Li and left eye and right eye inclusive, and also each box gets at most one ball. So like you have a really long number line, and you have several constraints, like what this ball wants to get somewhere here. That's the first ball. Then maybe some other ball it wants to go somewhere here. Don't necessarily need to be like that. They may like be completely within each other, or they may be, maybe they don't even intersect at all, so that's just like making our life easier. So we want to determine whether there is a way to put the balls into the boxes such a way that each box gets at most one ball, and also like each ball gets within its range. And a very common way to solve such problems is some sort of sweep line algorithm. So that means that we are going to process these ranges in some sorted order. Usually we do process them in sorted order of the left endpoint. So we're going to create several like events that at these positions the corresponding ball gets added into like our pool. So what happens is we go, like imagine walking over this line from left to right. Whenever you cross such a point, you pick that ball. Let's say initially all balls lie in some huge bag, and you're picking them one by one from there, and you're also putting them one by one into the boxes. Like whenever you cross the left end point of the interval, you take the corresponding ball out of the bag. So like here, we do get this ball at our hands. And we may immediately put him down, right? Because that's what we want to do eventually. So that's one thing. And when we, let me actually leave it here. When we cross, when we are putting it, imagine that situation was like if we passed one endpoint, we got one ball, when we placed it, it's fairly easy, right? What happens if it's not that easy? Let's say, let's actually get rid of that and see what happens here. So like we passed this endpoint and we got not one but two balls at our hands at the same time. Like how do we decide which one we are going to put first and which one we are going to save for later? That is another interesting thing. Like usually such ties get decided over the right endpoint, because if you think about, like, we have a smaller range for the green one, right, that ends here, and the larger range for the red one that ends all the way over here. So like, what's the point of placing red down first if it's like less strict to the range, about the range that it wants to go in? So let's just place the green one down and then take care of the red one later, right? Makes a lot of sense. And you can actually prove that that's like optimal strategy. So you just want to place whatever ends first, you want to place it first. And you can prove that by like just imagining that certain arrangement works. Considering this arrangement, considering two balls that got in the wrong order, and you can just swap them, and you'll see that the resulting arrangement is still valid. That's why such a greedy, you may call it, approach, it just always works, because you can prove it. Not all greedy algorithms work, but some of them do. And in this case, it should be fairly intuitive why this should work. And the reason why I really wanted to share this problem with you is because such concept of like sweep lining, I call it, some people I've seen on Codeforces call it like event processing, because for each segment you get two events, like left endpoint and right endpoint, and technically when placing down a ball, we should check if it's within the right endpoint. But at least this is the way that we are going to implement. Like imagine getting a lot of balls. Let's say this also starts here. So like we get a lot of balls at our hands. And imagine that the right endpoint is actually not that long. So let's say they are all of length 2. Let's say. Right, so we try our best. We place the green one down. If there are like literal ties and we don't care which one to pick, let's say we place the orange one, and we try to place the red one, and it is at this moment that we know that we did something wrong, because it does not fit within the range. So like this is one way to implement it, to just check when you are putting a ball down to check if it fits within the range. Another way is to like explicitly create an event for each right endpoint that checks that this ball is put down by this time. Like here you may find your mistake later than earlier. This does not matter for the correctness of the algorithm. And I'm assuming that this part of the implementation details will be clearer when we take a look at the implementation section itself. Like just to let you know that there are different ways to implement this. You can create one event for each interval only for the left endpoint, or you could create two events for left endpoint and right endpoint separately. Does not matter too much. And this is why this technique is sometimes called event processing, or at least I've seen one or two blogs in Codeforces on this matter. But yeah, the idea of just like generally going from left to right and processing segments in like increasing order of either their left or their right coordinates is just very common in interviews. I believe I've seen like a lot of questions on LeetCode, like let's say 5, which is a lot, I think, about this technique. And it's usually concerned with intervals and putting something into them, or let's say doing tasks within some certain intervals, or attending certain events during the intervals. That actually reminds me a lot like of the problem from the LeetCode when you had certain events and you for each event you had to pick a day to attend this event, and obviously you can attend only one event a day because according to LeetCode you're not very let's say productive. So yeah, or maybe you just want to really get really deep into this event, so that's why you can attend only one event per day. But regardless, the point was that this is very similar to that, if not identical. And it may be better to take a look at the implementation, because like the general idea, I suppose, is very not hard to get a grasp of. And you really want to know like what you want to find your way of implementing it, and then you'll be able to just like implement a bunch of problems in the same way. So that's why I really want to show implementation on this one. It's quite short. What we do, like, obviously we have to read some input. That's not very interesting. And I do create a map of events. Now, because it's a map, it's going to be sorted by default, but sometimes it's better to create a vector and then sort manually. I assume that vector plus sort is usually faster than map, because map obviously has to maintain a tree-like structure, which is more expensive than just having an array and sort it once. But a good thing that map lets you do is lets you group events into, let's say, a vector. So when processing events, you know that you are going to process all events from this coordinate, and I find it like very nice feature of using a map here. So what we do, we create one event for left endpoint. We just push the index, because index helps us restore everything from left-right vector. And also for convenience, like sometimes you want to create sentinel events just to make sure that you process all the info in your like algorithm. And we'll see why this is important later on. And I also create a sweep line, which basically means the position that we will try to place a ball in, and hopefully it will be within the range. I also have a priority queue of active segments, so like balls that we have at our hands that we have not placed down yet. And it's a priority queue because I want quick access to the minimum element. So yeah, that's why I used priority queue. You may use std set, it doesn't matter too much. But priority queue is a little bit faster if you want access to only like minimum, but set is more powerful, of course. So what we do is we loop our position x, and all segments, L is a vector. And by the way, if your collection that you're iterating over it contains other collections that may be potentially large, it really helps to have to loop with reference. So just nice thing that you should not forget. And also, obviously, auto for structured bindings is more or less the only type you really want to type here. Because the explicitly mentioned the type of such binding I think is quite hard, because I think that's like an iterator to something you really don't want to do that. So yeah, const auto reference is helpful, and constant is just like visual marker for yourself that you don't want to modify this thing by accident. I find it quite useful, because sometimes I just make a typo and I try to modify a variable. Let's say I had like left here that I don't want to modify and right that I wanted to modify. Then like I could make a typo and change left, whereas I really wanted to change right. And having const in such cases helps, because you understand that like compiler tells you that you're doing something wrong. So yeah, like having const in various places may occasionally save you from like hard to debug typos. So what we do with such events, we try, like first thing we do is we try as long as our sweep line position is less than our current position. So like it's less, so it means that we can't use the current balls. So this part corresponds to processing the balls that we got at the previous position. And we try to slow them into positions at sweep line if we can, if it's valid. So if this condition is false, then it's valid. It means that active top is the right position, as you can see here. So if this happens, it means that we are trying to place a ball which range ends at active top into position sweep line, which is basically invalid. Therefore, possible becomes false. Otherwise, it's obviously valid because its right endpoint is at least where we want to put it, and its left point is at most where we want to put it because of this this line. So yeah, we are trying, as you can notice, the element with the smallest right position. Then we go to the next position and we get rid of this. Now these two updates can be performed in any order. I assume it could have been actually clearer if I was to put if I've put it here. Because I could solve the work with sweep line in the same place. But this happens like we already processed, hopefully, all balls from the previous position. So now we can't, and now we got our hands on new balls. And these balls, they can get only into positions X and to the right. Right? Because they start at X. That's the meaning of events map. That's why we need to update sweep line. And we push their right endpoint into our priority queue. And that's basically it. It actually took me quite some time to get the implementation right. Because I was not using this map, I tried to store all events in a vector, and it was fairly annoying because I also tried to create 2 events for each interval, which was not worth it completely, so yeah. What you really want to do is you want to use map, I believe, because it groups events nicely for you. You don't have to think about it later on. You can just write your for loop and be sure that all events that start here get processed here and not somewhere else. Like you don't need to look at the next element and stuff like that. And the reason why this was important is because it just so happens that we first process elements from the last iteration, and then we add current elements. So these elements have to be processed somewhere. And that's why I added one extra event, not to process them outside of the loop with pretty much the same code. I really wanted this loop to be, like sometimes you need to process the last element separately. That's a really bad thing, I believe, because it basically increases the chances of making typos somewhere here or in the same thing here. Like in geometric progression, like the more things like that you do, the higher the chances. So yeah, I prefer using sentinel values, so having my code duplicated. So yeah, that's just like a really common thing to encounter in interviews. There will be a link to this submission down in the description. But we'll now get to the next problem. And this one is a little bit more on the competitive side. I have not seen that ideas occur that often in LeetCode problems. But let's first talk about the problem. This problem, which comes from Panasonic sponsored contest 2006. Problem E divide boss, we want to count the number of pairs XY in some range from left to right both of them in such a way that, well, their greatest common divisor is first of all not equal to 1, and second of all it's not equal to neither of them. We have our X, Y, they have their greatest common divisor, which is G, and what they basically saying is X is some let's say I don't really know. AG, A is some coefficient, and Y is some BG, A and B and G are greater than 1. So like maybe this is like something like 2 times G is 3 times G, and then G is not equal to 1. So yeah, this is like a counting problem that is completely abstract, so I believe it does not appear in the interview setting. And at first it does not sound like very easy to count such things. So what we need to do with such problem is to make a range, like a sequence of simplifications that are going to make our counting easier. So first of all, like this condition means that numbers are not coprime. It's very likely that you are going to need at some point to count how many pairs are coprime at some point. And you may remember something like other tangent function. I actually never I don't know how it's pronounced, to be honest. Funny thing. No, I never used it like in speaking. Oh, I'm not going to hear it. I'm not going to hear it. I need to change that. Oh no, that's Latin.
Euler's totient function.
Totient. Okay, yeah. So that's a tricky thing about English. Things may get pronounced not the way they look, fortunately. So this thing counts like how many numbers are coprime to some value. So you could count it with that, but what we are actually going to, you just need to compute tangent function quickly, you would need to factor numbers. So that's why we have some sort of a sieve in our implementation. But then you may know if you've taken some number theory course, but I assume that you don't know, because that's a rare knowledge, that certain sums with Euler function get translated very nicely into Möbius function, because there is a thing called Möbius inversion formula that transforms certain sums into nicer looking sums with Möbius function, something like that. And it also requires sieve to get computed quickly, but we'll the links to this to Wikipedia articles will be down in the description as well, because we'll need them as a background information on number theory to solve this problem, unfortunately. Like I try to pick problems that do not require lots of like prerequisite knowledge. When you don't need to like think very deeply about something, but you just need to know a certain fact or formula or something like that. But obviously such problems do come up in contests, and I assume that you want to know how to solve them, so that's why I wanted to share this one as well. Sometimes you gotta do what you gotta do, unfortunately. So yeah, we kind of have some ideas, at least, what is going to happen to the case g equal to 1. Another things that happen here is like x is not equal to g and y is not equal to g. That is also not very difficult, because like how to count such things and exclude them. So let's say we have x equal to g. G is at least 2 because g is not 1. How to count how many values of y are divisible by g. because what we really want to do is for x and y to have GCD of g. So because x is equal to g, it means that y should be just divisible by g, which is just like a very clean formula for that. Is right over g rounded down, and then technically like you want to exclude certain values, like you want to exclude the pair x or gg itself. So yeah, so that would be -1. And such thing that is like how many bad pairs you have where x over g is equal to 1. That's for a fixed value of x, and for all possible values of x you would need to subtract this sum from g, let's say equal to, first of all, it's at least 2. Also, it's at least left, right? Go all the way up to right, and we said we count right over g -1. So we kind of tackle the parts of this sum separately. So it may sound a little bit scattered all over the place at the moment, but believe me, it is going to change quite soon when we get a better understanding of what's going on in this problem. So this kind of that is just like one part that we are going to combine later on. I probably should have started with like simplifications that I was talking about. One of such simplification is that we can assume that x is at most y, or we may assume that x is less than y, and then just multiply the answer by 2, because we can the pairs are not ordered apparently. But if we assume that x is less than y, then y is clearly not equal to g, and you can get rid of this part. That's the real point behind assuming that x is at most y. So now we have this assumption. We remember that we have to multiply our answer by 2. And we have such two constraints, like count number of pairs with GCD not equal to 1, and such that x is also not equal to g. Well, x is equal to g, we counted here. So now what we basically want to count is like how many pairs of not coprime integers we do have. Well, if two numbers are not coprime, it means that they have some greatest common divisor. Let's say it's g, right? Now we want to know how many pairs have such GCD. We can't unfortunately answer this question directly. So the question is how many pairs xy there are in this range such that their GCD is equal to g. Unfortunately, I don't know a quick answer to this question. What I can tell you instead is how many pairs there are such that g divides x and g divides y. So like both x and y are divisible by g, because that's just much easier to count. You may say like, wait a second, that's the same thing. It turns out it's not. If you take x and y to be like 2g and 2g, their GCD will be 2g, not g. So we will overcount for a second, because we are going to count pair 2g to g for both g and 2g here. But we'll take care of it later. first we need to answer the question how many pairs of x and y in this range there are such that they are both divisible by g. And if you said that this is binomial coefficient from right over g rounded down minus left minus 1 over g rounded down by 2, then you're right, because this value is how many numbers divisible by g there are in this range. Actually, this value, it means how many numbers divisible by g there are up to right. And we subtract the values up to left, not inclusive. When we take this range from 1 to right, we subtract range from 1 to left minus 1, we get a range from left to right. That's like very, very common range arithmetic, if I may say so, because that's a little bit informal. But yeah, and then we have that many values, we can pick arbitrary pair ordered, so that corresponds to binomial coefficient. So one could try the following formula and just sum this thing from g equal to 2 all the way up to g equal to right. One could try this, but as we already said, that leads to severe overcounting. When you can't pair 4 and 4 twice for both g equal 2 and g equal 4. Well, let's not say 4 and 4, let's say 4 and 8, because we assume that x is strictly less than y. So pair 4, 8 gets counted for both g equal to 2 and g equal to 4, which is not great. We would like to count it only once, and here we'll need to get into some number theory to answer the question of like how many times we actually count this number and how do we account for that. We'll use some sort of inclusion-exclusion here, with the idea of like counting everything exactly one time. All right. So imagine we have a pair xy, for which values of g it gets counted at the moment. Imagine that their greatest common divisor is some value k. How many times we count them? Turns out we count them once for every divisor, for every g dividing k. So basically we count them however many divisors they have, right? That is not ideal, and that is not ideal. You'd like to count them only once overall. How to deal with that? Well, that's where like sum of something over divisors. It resembles a lot Möbius inversion formula. So basically we would like to when we consider a divisor, we would like to account for that. Take it like in inclusion-exclusion formula, if you remember, we take things either with plus or minus, right? Depending on like whether we need to add this part or take it back. Here we are going to add like plus minus sign here. It will depend on g. Namely, what I believe happens is that we use Möbius function, Möbius mu function of G here. Just multiply it. And that will be the sum. Now, I probably should define what Möbius function even is, because that is not a common knowledge. So imagine that we have some number n with a factorization like that. So it's p1 to some prime exponent v1, nu1. That letter is actually nu. Then we have p2, nu2, etc. P, let's say m, nu m. I will compress that in a second. That's a bit more. All right. So Möbius function is defined as follows. First of all, it's -1. No, first of all, it's 0 if any nu I is greater than 1. So like if your number is divisible by square of some prime number, then this function is 0. It's -1 if m is odd, and it's +1 if m is even. Alternatively, you may say that every number divisible by a square of a prime, the Möbius function is 0. Otherwise, it depends on it's -1 to the power of how many prime divisors we have. Now, we would like to understand why this construction even works. So basically, what we are looking for is here we want some function f of g, such that sum of f of g over divisors is equal to 1, right? And the reason why we use Möbius function is just because, like, on one hand, it may be well known to you. Well, it may be well known that sum of Möbius function of divisor of n is equal to 0 if n is greater than 1. But remember that we do not count g is equal to 1 here. So that's why this sum is actually, it's actually -1, meaning that we want to take negative Möbius function here. So yeah, like I just know this fact, so that's like, it was more or less clear to me after like 10 or 15 minutes. I remembered that I know such a function. It is Möbius function. Yeah, but there is also a combinatorial argument to that, like how do we decide which guys we include and which guys we exclude in the inclusion-exclusion formula? It was like, we would try to start with including all primes, but then we have to exclude our numbers of the form first prime times second prime and stuff like that. So that leads to this idea. Now, 0 in squares is like technical thing. It just gets discovered as you work your way through to this function. But yeah, generally I would say that this problem did require you to know about Möbius function, because it's really hard to come up with it in a contest that is like 100 minutes long. Given that is like not the last problem even. So yeah, I would say that this kind of a formula was kind of like prerequisite knowledge, unfortunately. So yeah, but once you know it, you kind of like understand. Well, I was looking for a function that behaves like this, and this is the function that I need to count everyone exactly once. You may verify that every number indeed gets counted exactly once. Every pair xy gets counted exactly once if you count them like that. Obviously, this definition requires you to know the prime factorization, so that's why we run our sieve. So yeah, and then we'll remove the blue sum that counts like cases where x is equal to g, and we also multiply the answer by 2 because to account for cases where y is less than x. Let's take a look at the implementation. So first of all, we have our sieve, which instead of just computing if the number is prime, it also records its prime divisor, namely its smallest prime divisor, I believe. Or maybe not, maybe it actually computes largest prime divisor. Not sure, I think let's say it's some prime divisor, let's not say like which one. Because I believe it may be incorrect to say that it's always like the smallest or always the largest. So as usual in the sieve, we loop over until up the square root of something, and we loop over multipliers efficiently. Just mark this is a condition for number d being prime, and this means that m got a prime divisor of d. And we have our Möbius function that works as follows. So first, we would like to compute the factorization. For this purpose, I often use an ordered map that stores like factor, prime factor, and then its exponent. So while the number is greater than 1, I check like if I already seen this prime factor in my factorization, then I can immediately return 0 from my Möbius function. But normally what happens is I increment the exponent and divide number by its prime divisor. And I check if the size is odd. It means if number got odd number of different prime divisors, different because we never hit this branch, it's all different. So then I return -1, otherwise I return +1. And here I just count. So the way I count, I take this a, that is like how many numbers divisible by k we have in this range. And I consider all pairs, and I multiply them by Möbius coefficient. And then I also remove all guys that correspond to x equal to g and multiply by 2. The implementation side is very short. Unfortunately, that Möbius formula is something you need to know in order to solve this problem. So yeah. The point is that like most of the time, good problems do not require you to know some textbook stuff, or at least the problems that I consider good do not require such things. However, sometimes there is no other way. You just get to know something, and it is kind of expected of like harder problems. To be fair, all problems that we have considered in this series, they are tough. Like, I recently discovered that majority of Codeforces users, they are like a pupil or below, which means that expert level problems, which I believe what bluish problems on AtCoder correspond to, they are just like very hard for majority of competitive programmers or people who just do it from time to time for fun. So yeah, like I'm not going to say that this problem is pretty, but if you want to solve such problems consistently, the number theory one specifically, then I believe that you do need to know some theory, unfortunately. That's how life works. Not all problems are like mathematical puzzles that you can come up with the entire solution during the contest. So yeah. On the other hand, once you do know the theory, it becomes significantly easier to solve certain classes of problems, which I believe like what Möbius function is about. Like you're not going to solve a lot of problems with it, but when you do face such a problem, it will be like practically impossible to solve it the other way. And this scenario, like remember I said something about Euler function? Like you may have thought that you could like compute Euler function to count how many numbers are coprime, but remember that you need to count coprime numbers in range, which becomes like practically impossible with Euler function, or at least I don't know how to do that. So it was not one of the possible solutions. It was like the only solution with the Möbius function, unfortunately. So yeah. I would consider this a positive thing because there is a limited number of such like textbook knowledge that you need to know, and then you're free to solve just puzzles, which I consider very fun and interesting. So yeah, hope you enjoyed today's episode and learned something new. And with that in mind, I will see you tomorrow with more AtCoder problems. And then on Thursday and Friday we'll switch back to code forces because I will be hopefully done with my upselling of recent AtCoder. So yeah, bye bye, see you next time.